this, so.
Yep.
But I will be available for a little bit after class too, if we don't get to your favorite homework problem. And I think, Alvis, your first one was 6. Is that what you said?
Yes, I think I was. Actually, let me double check the page. Okay, yes, I was able to get 6A, I think, finding the bounds, but not 6B.
Oh, okay. So if I remember correctly, in 6A, the bounds are between, plus or minus the square root of 3h bar over m omega or something like that.
Oh, yeah. I forgot to take the square root, but otherwise, yes.
Yes, because when you set energy equal to potential energy, there's an x squared in the potential energy. Yes. Okay, so B, calculate the probability of finding the particle in the first excited state of the harmonic oscillator outside of the classically allowed region. So if I were to sketch the potential energy, it looks like this. And here we are in the first excited state, so we could call that E1 for the harmonic oscillator. This region out here and this region out here is the classically forbidden. Oh, I'm sorry. Yeah, outside the classically allowed region, which means the classically forbidden region. So I want to find the probability of finding it in the area that I've kind of shaded on the x-axis. And so what I'm going to do is just integrate over that area of psi star psi and see what the area under the curve is, right? And so in this case, let's see. You probably want to write down explicitly what that time-independent Schrodinger equation solution is as a function of x. And it has some normalization constants. Let's see, I guess I've got it above there on the sheet. So it would be m omega over pi h bar to the 1/4. There's all these annoying normalization constants. 1 over the square root of 2 to the n factorial. So for us, n is 1. So I get a square root of 2 to the 1. And 1 factorial is just 1. So that gives me a 1 over root 2 for the first excited state. H1 of c is just c. And so that gives me a square root of m omega over h bar times x. That's my H1 of c. And then I have e to the minus c squared over 2, which is m omega over 2h bar x squared. Okay, so far, that's just specializing to n equals 1 in the general formula. And then what we want is the probability density. So we want to take the magnitude squared of that. Let me just amend this. That would make this a square root there. That would make this a 1/2, right? 1 over root 2 becomes a 1/2. This square root goes away. This x becomes an x squared. And when I square this Gaussian, the factor of 2 in the denominator, it goes away. Okay, so far, Alvis?
Yes.
Okay, so now what I want to do is, in this case, the probability densities for all the psi, lowercase psi n's, the definite energy states, are left-right symmetric. So if I calculate the probability of being in this region, I can just sort of double it to get the probability in being both those regions combined, or either one of those regions. So I'm going to say the probability that's asked for is 2 times the integral from this location. And if I remember, I'm assuming my number there is correct. That's the square root. Somebody tell me if I'm misremembering. 3h bar over m omega
Correct.
to infinity. And then I'm doubling it because it's going to be the same probability over there on the left of this thing squared, right? So I guess I should put all my constants out in front. I've got an m omega over pi h bar to the 1/2 power times a 1/2 that would cancel this 2, okay? Times another m omega over h bar, and then the x dependence, which goes under the integral, 3h bar over m omega to infinity, x squared e to the minus m omega over h bar x squared. Oops, x squared dx. So that's what I've got to compute. And we can't use our Gaussian integral tables, right? Because the Gaussian integral tables are only from 0 to infinity or minus infinity to infinity. They don't cover cases where you go from some finite value to infinity. The only reasonable way to do this is numerically. So you could use Wolfram alpha. You could do it in your calculator that way I described in an earlier assignment. The only difficult part is, and probably, you know, if you're in Wolfram alpha, it allows you to put constants in here and in here. But it makes a little bit more sense if we could get rid of those constants and exactly the right, if we change variables here from x to xi. So if we say, I've undone the x's, but now let me say, let's define xi to be the square root of m omega over h bar times x. I'm just going to change integration variables to xi. Then d xi is equal to the square root of m omega over h bar dx. And when, well, first of all, when x goes to infinity, xi goes to infinity. So that means the upper limit's going to stay the same. And when x goes to this value, there's some cancellations that happen in the xi. When x is this value, xi is actually just √3. Okay, so I'm just changing variables to xi, and I'm going to integrate from xi equals √3 to infinity. Let's see, this m omega over h bar times x squared is exactly what xi squared is. So that's xi squared. And then this was e, if you work it out, or where it came from, was e to the minus xi squared over 2. Okay, so that's substituting in stuff, everything except the dx. And now we're finding out the dx can be exchanged for a dxi as long as we put a square root of h bar over m omega out in front. So I guess I've already included this stuff that's sitting out in front. And I'm going to put a square root of h bar over m omega. Okay, so if I bring this down, I have the square root of m omega over pi h bar. Lots of stuff cancels out there. I just get 1 over the square root of pi. So I think after all of the dust settles, we want 1 over root pi times this integral. And that integral is easy to sort of do numerically because there's no undetermined constants in it. Although you probably could just put this into Wolfram alpha and it would spit it out in terms of the constants. So you have to get a number for this, you know, decimal approximation. Yeah. That was, so we, you know, when we change variables, right, u substitution, we say when x is this value, what is my u, or what is my xi here? So when I plug in x equals √3 h bar over m omega, here's what Xi is. And all those symbols cancel out, and we're just left with the square root of 3. Yes? Mm-hmm. It comes from the, let's see. It came, I actually don't know. It shouldn't be over 2. I'm thinking before I squared it. Yes. This thing right here is exactly Xi squared. Yeah, so there's no 1/2 there. So it's even simpler. Still got to do it numerically though. Okay, any more questions on that one? I think, Elvis, you also mentioned 8 and 9, so maybe we can just talk about how to get started on those. Is that correct?
Yes, that's correct.
8, for a particle of mass m in the harmonic oscillator potential, let psi be a linear combination of the nth and n plus first states in a certain way. Are you okay with the normalization?
I got as far as getting the integral set up, and then I had a hard time actually doing the integrals.
Yeah, so
Right.
we probably want to use the fact that these psi n's with all, with these annoying constants out in front of it are already normalized and they're orthogonal to each other. So that means the inner product of psi n with psi n plus 1 is 0. Okay, let's see how that comes in here. Let's demand that the integral of the magnitude of psi at time t equals 0 squared. Let's demand that that equals 1. And when I put in the expression there, minus infinity to infinity, in this case, we get integral minus infinity to infinity at 0. Let's see. I'm going to have a psi star times a psi. That will give me 2 factors of a. So I'll get an a squared, which can come out in front of the integral. And I'll have a 2 psi n star of x. Let me just not put the x in there. Plus 4 psi n plus 1 star. And then I've got to multiply by 2 psi n plus 4 psi n plus 1 and integrate that, right? There's my psi squared. We put the a out in front. We'll demand that this equals 1. So this simplifies to 4 integrals when I multiply this all out, or FOIL it out if you like. The first integral, so it's a squared times all of these things. I'm going to add the 4 integrals together. A squared times 4 times the integral from minus infinity to infinity of magnitude of psi squared, psi n squared dx. And that is going to be 1, right? That integral, because we've already normalized the state psi n.
Oh.
Okay, so this would be magnitude of psi n squared dx, right? Because I have a psi n star. So that's 1. So that gives me a 4 there. Similarly, for the last one, right? When I do psi n plus 1, I'm going to get 4 times 4 is 16 times another 1, because what will be left after I do the 4 times 4 is psi n plus 1 star, psi n plus 1 magnitude squared integrated from minus infinity to infinity, and that's 1 because it's already normalized. Okay, and then I'm left with the outer and the inner in the product. And those are both 0. Because we talked about how these states, I think, I didn't show it in class, but Griffiths, I think, shows or states, I can't remember what's in the book, but the various definite energy states are orthogonal to each other for different indices. So that means that, for example, the integral from minus infinity to infinity of psi n plus 1 star psi n dx is equal to 0. And that's the kind of integral you're going to have in outer and inner. They have different indices. So outer and inner give 0. And then, so what do we have left here? That's 4 plus 16 is 20. So that means a squared times 20. And we're going to demand that that equal 1, should equal 1. And that means a is 1 over root 20. Okay. I'm just looking at B, C, and D. If we measure the energy for a particle in this state, what values might we get and with what probabilities? That one you don't have to do any calculation. When I look at this state right here, what I'm seeing is really, I'm seeing my initial state. It's as if I'm seeing this written out. The sum from 0 to infinity of Cn psi n of x, right? Except that this is really an infinite series, except that all the terms in the series have coefficients Cn, which are 0, except the nth term and the n plus first term. Okay, so this is saying that once I take into account that a is 1 over root 20, then I can sort of, I can say what my state looks like this. 1 over root 20 times 2 psi n plus 4 psi n plus 1. Okay, so I'm thinking of that as an infinite series, except only 2 terms have non-zero coefficients in front of it. So all the Cn's are 0, except Cn and Cn plus 1 for whatever n is, right? So I would say Cn, for whatever the number n is 2 over root 20. And Cn plus 1 is going to be 4 over root 20. And then how do this is phrased in terms of probabilities. So it looks like the only non-zero probabilities are associated with En and En plus 1. So En has a probability of what? And En plus 1 has a probability of what? Well, it's just the square of the Cn and the Cn plus 1. So this would be 4/20ths. And this one would be 16/20ths. And notice they add up to 1. That makes me feel good, like I didn't make a mistake there. Okay, so only 2 allowed energies that, if you measure the energy of this state, you'll only get one of 2 values, and you're much more likely to get the higher energy value than the lower energy value. Okay, and then C, you're going to put in the time-dependent factor on each one of these 2 things, right? The usual time-dependent factor. And then in D, you're supposed to compute this with the time-dependent factors in it. And you're going to find in some, when you FOIL it out or multiply it out, distribute, you will find some of those complex exponential things will cancel, right? I might have an e to the plus I en and then an e to the minus I en kind of factor, and they would kill each other in one of the terms. But in another one, I might have an e to the plus I en plus 1 times an e to the minus I en, and those won't kill each other off because they're not inverses of each other. And then show that the probability density oscillates in time sinusoidally. What that means is that when I simplify out the magnitude of psi of x and t squared, I should get something that looks like a constant plus a sinusoidal term. So it's going to oscillate. The energy is going to, the probability density is going to oscillate in time sinusoidally And the frequency at which it oscillates should be the omega that comes into the potential. In other words, the omega that comes into the, n+1/2 h bar omegas. So what that means is, as time goes on, well, I showed you this Java applet, if I may, again. The sinusoidal oscillation just means at any location in space, it should oscillate sinusoidally. So let me see if I can find a link to that Java applet. I don't have it open, do I? No. Somewhere in here, I've got a link to it. Not there. I know I do later on down here. Somewhere here, there we go. Let's go and look at the harmonic oscillator bound states. Let's get rid of some stuff on here. So what I'm going to do is say, these are all the definite energy states that we're seeing in yellow right there. Let me put it in, so this is sort of, right now it's in the ground state, and this is the associated probability density shape down below. I can tell it's in the ground state because I can see only this first kind of phasor thing that's moving around in a circle is highlighted in white. Instead, what I'm going to do is clear it out, put an admixture of this phasor, which is like, n = 14 or something like that. Okay, and n = 15. Now notice when you look at any point, so the probability density, it's not in a stationary state, so the probability density is changing with time, right? But look at the height at any point on the x-axis, and you'll see that it looks like it's bouncing up and down sinusoidally, at least it's believable. So what I mean by that is the probability density is a constant plus a sinusoidal function of time, and the frequency should be exactly the omega that appeared in our potential energy. Okay, maybe that's enough or too much on that one. And then what is 9? Alvis also asked about 9. Suppose a particle of mass m and a harmonic oscillator potential is in a Gaussian initial state. Give a formula for the normalized version. So you would use your Gaussian integral table that we linked to, or it's in the back cover of Griffiths too, in a slightly different kind of way of writing it. Find the expansion coefficients C0 and C1 explicitly in terms of m, omega, and alpha. So maybe we can just talk about B. How would I find C0 and C1 for this initial state in 9 that's a Gaussian? e⁻⁴ x squared at time t = 0. So we're saying our initial waveform at a certain time we're calling t = 0 has this shape, e⁻⁴ x squared. And we're going to determine the appropriate constant to put in front of it. So the area under the square of that function is 1, right? Then we have a normalized waveform. That's A. Then B is find C0 and C1. So that means I need to write this as a sum from 0 to infinity Cn psi n of x for the harmonic oscillator psi n's. Okay, so how do I get, for example, C0? Let's just see if it looks doable when we get this. What do I do? What's the prescription? Somebody help me write down the formula here. Integral. So I have x0, so we have our a e⁻⁴ x squared, yeah? So that's psi at the initial time, whatever it is. Here it's t equals 0. Times what? Yeah, times little psi 0. In other words, to get Cn, I would put psi n star there. They're real functions, so I don't need to worry about the star in this case. So it's sort of a pain, right? I mean, there's that thing to the 1/4. There's a 1 over the square root of 2 to the n factorial, but 0 factorial is defined to be 1. 2 to the 0 is 1, so that square root factor is 1 there. And then I have hn of xi, which is 1. That's my hn, written as a function of x or xi. It's 1. And then I have e to the minus xi squared m omega over h bar x squared over 2. And I have to integrate that with respect to x. So you can see, the goal here is just to not get too daunted by all the stuff and say, let's just see what happens. Can I do this integral? Here's a constant. I figured it out in A. Here's a constant. Let's pull those things out in front. Other than that, we've got some constants sitting out in front. We've got an integral from minus infinity to infinity of this Gaussian times this Gaussian, right? And when you have exponentials like that, you just add the exponents, right? So I'm going to get something that looks like e to the minus alpha plus m omega over 2h bar x squared dx. So I don't remember what it's called. I think in the integral table I linked to, this was called a, right? Whatever's in front of the x squared. So that's telling you what your a is, and then you plug it into the formula and figure out what it is in terms of those symbols. Similarly for h1, right? For h1, I'm going to have a xi here, which is an m omega over h bar x. And so I'm going to have to do an integral that looks like this. X e to the minus a x squared. And that's another one that appears in your integral tables. So you just sort of follow it through. You should be able to look up what those are in terms of the symbols that appear in A and the constants that I pulled out in front. Is that enough on those?
It should be.
Should be, okay. Well, so hopefully give it your best shot. I am going to, as I said, I just haven't gotten to it, but maybe I have an exam in my 3 to 4 class, so I'll take that time to post my solutions to these. I'm just trusting that you tried them already and you can look at the solutions and you'll write up a neat version and turn them in tomorrow at the exam of 1 through 9, right? Okay, good. I have a little bit more time afterwards for questions too. So if there's more, hang out. All right. Let's see. I have to back way up here. I think this is where I wanted to start out. If I remember correctly. Yeah. So just to remind ourselves where we were at before, we were talking about group velocity and phase velocity, and I have a worksheet I wanted to work on, but just to remind ourselves of the idea that, most of the time when you have at some particular time some initial shape, chances are the probability is not going to move with any sensible velocity. You're going to find that it just sort of goes up and down crazy all over the place, kind of like we just saw in that harmonic oscillator example. But sometimes in very restricted kind of situations, and we'll talk about where that is in just a second, you'll find that there are some wiggles, and what's important is that they're under an envelope. Here I've got sort of a double bump envelope, right? And so they're bounded on the positive and negative side between that envelope. And as time goes on, the shape of the probability density might change a little bit. In other words, it might flatten out and spread out or something, but it sort of mostly maintains its shape. And in that case, we could say there's some sense in talking about what the velocity of a classical particle that corresponded to that would be, because if this whole mess of probability is moving to the right at speed v, that's sort of what we think of corresponding to the classical speed of the particle. I don't really care so much about how fast these little wiggles and jiggles in here are moving, to the right or something like that. What I care is the big lump of probability. If it has a sensible velocity, then that would have to be the thing that corresponds to the classical velocity of the particle. And we said how fast the envelope moves, which corresponds to the classical velocity, is called the group velocity. It means this whole mess is sort of translating to the right. Not exactly, it might change shape slowly. We know it can't keep the same shape. If it kept the same shape and just translated along, that would mean that all the different wavelengths that I need to put together to make up that shape would have to move at exactly the same speed. And that would mean we're talking about a dispersionless wave or dispersionless wave equation. But we know, or at least we can show, I talked about this in chapter 0, the time-dependent Schrodinger equation has dispersion. So different wavelengths travel at different speeds. The bigger the difference in the wavelength, the bigger the difference in the speed. And so if you have a lot of different wavelengths, you're just going to see random motion all over the place. But if you have a narrow range of wavelengths, they'll all almost move at the same speed, except one will get slightly ahead as time goes on. That's going to cause the envelope to kind of deform as time goes on. And the example I showed in MATLAB, or it's MATLAB simulation anyway, was of a Gaussian wave packet where the envelope was like a Gaussian shape, and underneath there was this faster frequency kind of oscillation. So the e to the ikx is the, spinning around in the complex plane, but it's modulated by that Gaussian envelope. And if you, well, I guess I'll go forward to this. Here's a little animation that keeps repeating over and over again. What we're seeing is, the envelope, which is given by the blue shape, the actual complex wave function as a function of time is given by the black curve, which is shown winding around the x-axis and actually moving as time goes on. But the envelope itself is given by the blue curve. And you can see, yeah, it's deforming as time goes on, but we can sort of give a sensible velocity to that. And if we checked out what the spectrum is, we'd see there's just a very isolated range of wavelengths, not too many wavelengths involved here. And so they're all moving at approximately the same speed. And in this case, you can compare the group velocity to the phase velocity. The phase velocity is how fast those little wiggles and jiggles under there, the peaks are moving to the right as time goes on, or moving down and to the right in my image here. Now, it sort of looks like they're going backwards, but if you actually watch them, the peaks are actually progressing forward as time goes on. They're just not progressing forward as fast as the envelope is, right? So the lump of probability is moving with a certain speed. These little wiggles and jiggles are also moving to the right, but they're moving with less speed. The phase velocity is less than the group velocity, so they're sort of falling behind, which makes it look like they're kind of going backwards, but they're actually moving forward if you carefully watch where the peaks are as time goes on in that case. Okay, here were a couple reading response questions having to do with this. And again, I'm certainly not seeing everyone who has posted on this. This was section 2.4. I think there were 4 people who had responded. So try to keep up with that. It's not a huge part of your grade, but it's like it really can affect your grade if you just forget about it and don't do it for half the term or something like that. This is part of a larger, kind of discussion. This means that over time, the wave function becomes less localized and spread out. We just saw that with the Gaussian traveling wave, increasing delta x. But if we have a beam of electrons, for example, it seems like those particles stay localized no matter where they are on their path. It's always hard to tell what exactly people are thinking of when they're saying this, but that wave function that we were looking at as time goes on, whoops, this one here, could represent a single electron. So this is a perfectly valid state, watching it progress as a function of time for a single electron. Its probability density is sort of moving along at a sensible speed. Now it's changing shape a little bit as time goes on, but more or less we can assign a sensible velocity to it. And so, the electron's somewhat localized, but it's not definitely localized. There's still a little bit of uncertainty, and its uncertainty is getting greater as time goes on. Okay. In this case, the reference is being made to a beam of electrons. Now, that lump that we saw moving around there is certainly not like a beam, right? That would be like a very narrow pulse consisting of a single electron, right? But if you have a beam of electrons, you don't just have a single particle. You have essentially an infinite collection of particles that are sort of spread throughout space. And you have to think of it as a multi-particle system, which we'll talk about later on in the course. But for a single particle, there's no sense. I guess that sort of connects up with the second response here. If a free particle cannot have a definite energy, that's a statement that Griffiths makes. What determines how much energy the particle has? So why does Griffiths say a free particle can't have a definite energy? Just to connect back up to that free particle discussion. Can't normalize them, right? We solved for every single definite energy state, and they were all of the form e to the I kx minus omega t. So at any given time, it looks like e to the I kx. And if you take the magnitude squared of that function, it's just constant all the way out to x equals plus or minus infinity. So there's no way to make the area under the curve finite. It's an infinite area. And if you divide by the integral from 1 over the square root of the integral from minus infinity to infinity, you'll be dividing by infinity and get 0, which still won't be normalized. So if a free particle cannot have a definite energy, what determines how much energy the particle has? How would you guys respond to that? In other words, this shape, or going back to this is, I didn't put any potential energy here. So this is an evolving wave function for a free particle. Maybe it's an electron. It's in this state. How much energy do you think it has? How would you answer that question here?
Analyzing its frequency?
Yes, we would say the definite energy states are the states with a definite wavelength. They're the e to the I kx kind of states. So I need to figure out how much of all the e to the I kx's with different k's or different lambdas are needed to compose this using a Fourier transform. And the answer is there would be lots of them. And for each different k that I need, that's a different energy. So if you're asking about, where was it? What determines how much energy the particle has? Well, for example, in that state I was illustrating there would be lots of different energies that you might measure when you measure the energy of that particle. A particle, unlike in classical mechanics, doesn't have an energy in most cases. It's only the rare case. And what we're finding out here for the free particle, it can't have an energy. It wouldn't be in a normalizable state. It could be very close to it. But in this case, there are a range of energies. How long can a particle remain free before reaching a definite energy by entering a bound state? Well, in this case, again, there are no bound states, at least for the free particle. So it's going to remain free forever. And we would just say it's in a linear combination of different definite energy states. And there are no bound states to enter into. If there were bound states, it would never enter into them, because whatever the probability is of being in a certain definite energy state stays at that value for the rest of time. And so if it wasn't in a bound state to begin with, it's never going to end up being in a definite energy bound state after that. How can the phase velocity be anything other than the group velocity? the waveforms would move at different speeds than the particle and disappear or end off once they fail to stay contained within the particle. Is this true? Well, I think this animation, hopefully answers that, right? Here, the envelope is moving at a different speed than these. They're sort of falling behind the envelope, but they're not disappearing. I mean, they do get, as the bumps move back, they get lower and lower amplitude, but new ones appear at the front of the envelope. So I don't think there's any problem with that. It's just that usually when we're comparing, the point I think of this discussion is when we're comparing to what you know about classical particles and macroscopic motion, we should be concerned with the speed of the envelope, the group velocity, not the phase velocity. Okay. Just checking the time to see where we're at. Okay, so let me just summarize what Griffith says here and then we'll do the worksheet and see where we're at. Maybe we won't even talk much about Dirac delta scattering today. So we said in order to have a sensibly moving envelope, you've got to have just a small range of K values. The larger the range, the faster that envelope is going to change shape. And pretty soon it's just going to disappear almost right away. And making that assumption, Griffith says if you have a small range of wavelengths, then omega, which is a function of K, the omega, the angular frequency, which is a function of K that's involved in our phase velocity. Since we're in a small range of K, any function can be well approximated by, say, the first two terms in its Taylor series. So we're saying, let's write omega of K as the value at the central K value plus the derivative of that evaluated at the central K value times K minus K0. And run the thing through. And I'm not going to go through the details. Griffith shows that it ends up in this form afterwards. You make that approximation and try to do this integral. And what do we get? We get a product of two things. So we can think of it as an envelope. This is the envelope shape, modulating something that's wiggling underneath. And the thing that's wiggling underneath, you'll see, if you think about how e to the I kx minus omega t moves, this moves to the right at speed omega over k0, or omega over k evaluated at k0. That's the phase velocity that we gave before. And the envelope moves to the right at speed omega prime at k0. In other words, d omega dk evaluated at the central k value there. Okay, so that's telling us that those wiggles and jiggles underneath the envelope are moving at this speed, but the envelope itself is moving at a different speed, unless you're talking about a dispersionless wave. But this has dispersion when we're talking about the time-dependent Schrodinger equation. Okay, and in this case, we can go back to the case of a definite energy state for a free particle. We've got a definite energy state. The e to the, if you write it in the form e to the minus I omega t, omega would be e over h bar, and our formula for the energy states for a free particle is h bar squared k squared over 2m. So if I divide by h bar, that gets rid of 1 power of h bar. And therefore, if I do omega over k, that's the phase velocity, omega over k, I'm going to get h bar k over 2m. Okay, so the phase velocity is h bar k over 2m. But if you calculate d omega dk, you pull down a power of 2 when you take the derivative with respect to k, and you get this factor of 2 difference between the group velocity and the phase velocity for a single energy state. Now, granted, a single energy state doesn't look like an envelope, an envelope that's moving in a sensible way, but at least it sort of makes sense that Griffiths observed earlier that the phase velocity seemed to have the wrong value, but if you calculate the group velocity, it actually has the value that agrees with the classical kind of case. Okay. Before we go on, let's do a worksheet. Any questions on that? The upshot is just those two formulae, omega over k and d omega dk, which I assume you talked about in modern physics, right? Phase and group velocities having those formulae. Where are my worksheets? Here they are. So here is a particular initial wave function shape for a free particle. We're supposed to find phi of k, and maybe I can move the slides back to where the formula for phi of k is. It's like the other one, but it's got that factor of 1 over root 2 pi in it. And then at the bottom, you're asked about the phase and group velocity, thinking about this kind of case. So in this particular weird. Okay, let me move this back to the point where it tells how to calculate the phi of k's. It's not too hard to remember that formula. Here it is right here. That's what you're supposed to be doing in part A. And then B and C, you're supposed to be thinking about group and phase velocities. Somehow I've misplaced something, so I'm going to run back to my office and see if I can find it. There's a different Gaussian integral there, which is related to the ones in the table. You could actually prove the one that I'm giving you here by completing the square on it, but you're just supposed to use it here. Okay, I know time flies when I'm having fun, and probably let's just talk about this together. Hopefully you've gotten partway through this integral here. I've written out just, what was given there in terms of our function translated into that formula for phi of k. So this is the integral we have to do. I can pull this constant out in front. So it's 1 over root 2 pi, 2 lambda over pi. And then I'm just going to combine this together into one grand and glorious exponential function. So I get an e to the minus lambda x squared. And let's write it this way. I'll factor out the minus sign. So then I would have a plus I k minus k0 x. Is that right? I have an e to the minus I kx and e to the plus I k0 x. So that looks right. And I think that's in the form of an dx, integral of this dx. And that's of the form that is in that given integral. So this lambda is my a in that. And my b is all of this stuff, including the I. Okay, so let's not sweat the details here and just try to write down what, plug it into the integral formula that's given there, 2 lambda over pi. I think one of the homework problems you might be asked to prove this integral property, but we haven't gotten to that one yet. Okay, so the claim is this is root pi over a, and a is lambda for us, times e to the b squared over 4a. E to the b squared, but I squared is minus 1. I have a k minus k0 squared. So that's b squared over 4a, and a is lambda. I think that's right. Okay, so that's phi of k. And I guess I can cancel out that root pi against this root pi. I can simplify a few things there, like I think this ends up being root 2 over lambda. No, I could even simplify it more than that. I have a lambda in the numerator, so root 2 lambda, does it really simplify down to that? Doesn't agree with what I have. All right, I have a lambda, and then I have a 1 over root lambda, which is a root lambda. Oh, a pi, yes, divided by pi. Divided by pi. Doesn't look like it quite agrees with what I have here, but I didn't quite simplify all the way. Oh, no, I actually agree. Yeah, that agrees with what I have here. Okay, times this exponent, Gaussian function. Okay, so now let's write down what phi of x and t is going to be given this. Forgive me if I want to keep it in the place where Alvis can see. Oh, and Alvis can't see. Hopefully he's maximizing.
Oh, I maximized it.
Yeah. I like to get it in the video just in case anybody ever watches it. Okay. Psi of x, that tells us how to write psi of x and 0 is 1 over root 2 pi times the integral from k equals minus infinity to infinity of phi of k, okay, that's root 2 lambda over pi times e to the minus k0 squared over 4 lambda. That's my phi of k times e to the I kx integrated with respect to k. Okay, and we don't necessarily have to do the integral. We could do this integral, right? I've really got a quadratic function up there, and I could complete the square if I really wanted to use my Gaussian integrals, but you're told you can leave it as an integral expression. That would be phi of x and 0. Now let's put in the time dependence, and that means each one of these gets the corresponding free particle phase factor going next to it. E to the minus I En is h bar squared k squared over 2m, e to the minus I ek t over h bar. That looks good. And that's my answer. If you really wanted to do, another half or a whole page of work, you could probably wrangle that into a form that you could use your Gaussian integrals on, but you'd have to combine this all into one exponent, square this out, complete the square so you have something squared plus a constant. It's kind of a mess. But you could if you were desperate. Any questions on that? 1 minute left. Okay, well, I think we have enough time to talk about B and C, just to point it out. Okay, the integral can be done. It has it's of the form when you do the integral of a Gaussian envelope times a phase factor that's wiggling underneath. From our discussion of group and phase velocity, with what speed would you expect the peak of the Gaussian envelope to move? Well, notice this is our omega here. Omega is a function of k, right? Sometimes people write this as e to the I minus I omega t. So for us here in this form, omega is h bar k squared over 2m. That's omega as a function of k. How fast do we expect the peak of the Gaussian envelope to move? We expect it to move with the group velocity, and that is d omega dk evaluated at the value of k that the group of wavelengths is centered upon, and we're calling that k0 here, right? In other words, as a function of k, this thing sort of goes down to 0 when you get too far from k0. So, okay, so d omega dk, that pulls down a 2 there. It cancels the 2 in the denominator, and I get h bar k over m evaluated at k0. From our discussion of group and phase velocity, with what speed would you expect the wiggles in it to move underneath the envelope? Well, that's just omega over k, and I can do that right here. If I divide both sides by k, that just gets rid of one of the k's there. And again, you're seeing that factor of 2 difference between the phase velocity and the group velocity for this, again, kind of Gaussian traveling wave. This example is exactly the one that I was showing in MATLAB. It's just getting the numbers out analytically. Okay. Feel like that ended with kind of a fizzle, but I don't know if people have fond memories of group and phase velocity from waves and modern physics, but we're slowly letting it sink in. We're going to go back to on Friday. So I sent out an email yesterday saying to do the reading for the Dirac delta function potential, which I thought we might get to today, but we'll definitely get to it for Friday. So do the reading, do your posts on the website, and we'll go back to good old standard solving time-independent Schrodinger equation for a different potential. And this is one you haven't seen before. So there's somewhat of a surprise, I guess. It'll be the first example where we don't have an infinite number of bound states. There will only be a single bound state for